Okay, so probability generally, so you have a sample space S that's going to be the set of all possible outcomes of a conceptual or physical repeatable experiment. So S can be finite or infinite. So it could be like if you have a dice, how many different possibilities you have. So 1, 2, 3, 4, 5, 6. It could be the set of all possible nucleotides in a DNA site. So like these values. And then it could be the set of all possible time-space positions of an aircraft on a radar screen. So that's like sort of infinite possibilities. And then an event A is any subset of S. So you can think about that as like seeing a 1 or a 6 on a dice roll, or observing G at a site, or like some specification for the time space position of an aircraft. Okay, and then there's so then the sample space is just going to be a collection of all the possible outcomes. So like the 1, 2, 3, 4, 5, 6 is the sample space S, and then the random variables, the random variables X, which is basically what we're going to be concerned with, is are representing the outcomes in the sample space. So how likely is it that something happens? So how likely is it that you roll a 1, for instance, is going to be like the random variable. Or I guess the probability is how likely it is, and then, or the probability of X happening, but X is rolling a 1 itself. And then the probability of random variable to happen is denoted by Px, where this is equal to, you can think of it as like the random variable equals that thing. So this can be like rolling a 1, X is rolling a 1, and the random variable is like assigned to that possibility or that outcome. And then you always know that the probability of any random variable has to always be greater than or equal to 0.
Can I ask a couple questions?
Oh yeah, okay.
Could you go back to slide 5?
Yeah.
Okay. Okay, then back to slide 6.
Okay.
I also want to make sure I get the terminology right. Okay, so the sample space, that's like either finite or infinite.
Yeah.
And then X, that big X, represents general outcomes or a specific outcome little. Is little x the specific outcome then? As opposed to big X, random variable.
Yes. Yeah, you can think of it like that.
Oh, I see. Okay, got it.
Yeah.
I just want to make sure. Okay, thank you.
Yeah. And I guess we'll talk more about this as we do examples and stuff. Okay, so then you have like two types of probability distributions, or probability random variables. You have two types of random variables. One is like the continuous variables, and the other is are discrete variables. And so for continuous variables, you have like continuous probability distributions. You'll usually have what we call probability density functions that like look sort of like this, or like have some shape to them, and you're sort of considering probabilities that are either like greater than X or less than X, and just different things like that. And then you might also have density or likelihood values. I'm not really sure sort of what he's getting at with all these different things below this continuous variables. I think maybe it's just examples of continuous variables and where they might come from. So like, for example, something like a temperature, which is a real number, is continuous. You don't really have like discrete temperature values. And then Gaussian distributions generally are like these sort of bell curves, and they're sort of by definition continuous. Whereas I think with the discrete variables, you kind of have something that looks like for some X, you have some like discrete probability, and then let's say there's some Y, you have some other discrete probability. So instead of continuous probability distribution, you have discrete probability distributions. Instead of probability density functions, you have probability mass functions. Instead of density or likelihood value, you have probability values. Example is a coin flip, and an example distribution is the Bernoulli distribution, which we'll talk about. And so for these continuous distributions, you basically have the integral over all probabilities for all sort of random variables or all outcomes has to be equal to 1. And basically the discrete analog is just the sum of all the outcomes. The sum of probability of all the outcomes has to be equal to 1. And then here's some examples. So like the uniform density function is where you have a uniform, basically a uniform probability for every single, and these could be like, you know, infinite or whatever, but every single value, every single outcome has the same probability. So you can I guess you can also think of it as like through some interval a to b, you have some uniform density of those of that probability. Hey, Kevin.
Hey.
And then so like the function probability density, the uniform density function is defined by this, where for that interval that you're looking at for x in that outcome of intervals, the density function is represented by 1 over b minus a. And here they kind of just show an example where you have the uniform density is 1/7, or the value of the uniform density is 1/7, and you have sort of 7 different discrete steps. And so, yeah, and then it's 0 otherwise. And then similarly, we can have other distribution functions, other probability functions like the exponential density function and the Gaussian, which is usually referred to as normal density functions. And I guess I'm not really going to go into details for the other two, but you can kind of, yeah, well, I mean, I guess we'll talk about Gaussian distributions later. We won't really talk about exponential, but I think the idea is basically the same. You have some function that describes the probability of each outcome, and that's how you kind of that's how you kind of evaluate probabilities that are that's how you evaluate the probabilities of outcomes using that function. And then for discrete probability functions, you have we have some examples. So one is the Bernoulli distribution. So for this, you can think of it as like a coin flip. So you have some probability that you're going to. So you have basically two possibilities. It's a Boolean, so like true or false. And so you have some probability that's going to be true, and 1 minus that probability that's going to be false. And so in this Bernoulli trial, just a single trial is conducted. So you basically have one coin flip, and you have probability for that being true and a probability for that being false. And then sort of going from there, you've got to think about a number of different trials, and not just one trial, but n number of trials. And you can have a binomial distribution where you still have like either a true or false value. So P is still the probability that's going to be true, or the probability of success, and 1 minus P is the probability of failure. So basically, you have for this binomial distribution that you have this is like n choose k. So this is the total number of ways the total number of ways of selection k distinct combinations of n, irrespective of order. So how do I explain that better? Does that make sense, that definition of n choose k?
I probably need to see something written out. I'm not sure how easy it's going to be to talk about this through words. I've heard of binomial distributions, but I have to look at it to refresh.
Okay. Oh, did I stop sharing? My bad. Let me share this screen. Let me just share my whole screen as I move through. So this is kind of like the basically the number of times you can choose k out of n is kind of the idea. But yeah, so the formula can be understood as follows: k successes occur with probability k. No, that's not. That's the entire formula. But yeah, okay. So I'll go back and try to explain this better. But so basically, the binomial distribution kind of gets at how many, like if we want to say how probable is it that the number of successes we have, basically the random variable, is equal to k. So let's say we're going to roll a dice, or not roll a dice. Let's say we're going to flip a coin 10 times, and we want to know how probable it is that we have 7 successes or something, right? And so we can use this binomial distribution to solve that, because the probability is known. The probability is 0.5. So 0.5 times we're going to get heads, 0.5 times we're going to get tails. And so we can say, okay, how many, so let's say we're flipping it 10 times, so we have 10 choose 7 times probability of getting 7 successes or 7 heads is 0.5 raised to the 7th, and then 1 minus 0.5 of the failures, so which is n minus k, which is 10 minus 7, which is just 3. So that will evaluate to the probability of getting 7 heads if you flip a coin 10 times.
So the 10 choose 7 is not a numerical operation.
It is.
Yeah,
It is. It's represented by this. Yeah. So n factorial divided by k factorial.
Okay, thank you. Okay, I mean, I guess, okay.
Yeah, so. Just for future reference. Okay. So that's an example of these kind of discrete probabilities. So you'll just have basically, yeah, you have some fixed outcomes, and you can kind of think about distributions for those fixed outcomes and get probabilities from those distributions. Okay, and then now we'll talk about, I think probably these next two will be sort of the most useful parts of this: joint and conditional probability distribution, and then Bayes rule. Okay, so then he sort of gives an example here of 2 random variables, x and y. And x is the random variable for like throwing a dice, the outcomes of throwing a dice, so 1 through 6. And then y are the random variables for flipping a coin. And so you have some n number of trials, and n ij, so I being the outcome on the dice roll, on the dice roll, and j being the outcome on the coin flip. And so you have some nij number of occurrences of, for example, for 1 1, or I guess 1 2, n1 2 will be 3, because you get you had 3 times that you saw both a 1 on the dice roll and a tail on the coin flip. So you do these trials, and then you have some data for these. And so you can see basically the distributions for like, or the occurrences for these different things occurring. So like if you want to look at like the times you roll, number of times you rolled a 4 and you flipped ahead, you would get like this 2 value here. Okay, so then using that, we can kind of define these joint distributions. So you can kind of think about, okay, what's the probability that I roll a 1 and I have a tail? And so that probability is given by the number of times you saw that you rolled a 1 and had a tail, which is given by 3 here, and then the number of times total that you did the sort of experiment. And so, so the probability of that happening is just going to be 3 over the total number of like times you did the trial total. And then you can also define these conditional distributions. So this is joint, this is conditional, which is basically saying, okay, if I, yeah, so the way you read this is like, what's the probability that there's a head if I'm given, so for a particular trial, what's the probability that it's that the y is heads, given that I know the dice roll was a 1. And so another way to think about this is just flipping the, I guess, the order. So given that I know I rolled a 1, what's the probability that I flip ahead? And so this is given by the number of occurrences of both of them together. So this Nij of rolling a 1 and having a head divided by the amount of times that you rolled a 1. So divided by Ci in this case. Okay, and then I guess this is kind of, I don't really know how we would define this, but if you want to just know the probability of rolling a tail, flipping a tail, you can just add up all these probabilities of basically any x. So basically, there's 20 tails that are going to be rolled divided by. So this is equal to sum of all this, sum of p. I'm not really sure how to define it, but it's Cj, where j equals tail, divided by n, right? And so basically what this sum value is saying is that you sum up all the joint distributions of rolling a tail, flipping a tail for all rolls of x. So across all i's, you sum up the probability, the joint probability of rolling that specific x or that specific number and flipping a tail. And so that's going to be the total probability of flipping a tail. Okay, so then from there we can kind of talked about it, but we can kind of define these values. So probability of x being xi is going to be ci over n. So basically the number of times you saw xi divided by the total number of trials. And then joint probability, like we mentioned, is the probability of both these things occurring. So in these individual sort of cells, divided by the total number of trials. And the conditional probability, so yj given xi, is going to be what the probability of seeing both of those things happening together, which is the Nij, divided by the probability that, or divided by the number of times you saw both those things happening together, divided by the total number of times you saw xi happening, which is going to be Ci. And then there's some rules that we can sort of, I guess, derive from these. And one is kind of this last rule here, this probability of getting y tail. So the probability that x is equal to xi. So probability that you roll some out of these occurrences, the probability that you've rolled some number in the dice roll is equal to the sum of all joint probabilities across all yj's. So basically, across all coin flips, how many times did I see this dice roll? And so you can kind of like, if you kind of take out some of the, I guess a simpler way to express this is just by taking out these definitions, and you'll likely never really see this this notation of like x equals xi, and you'll just see it sort of shorthanded like this. So across all y, summing up the joint distribution of xy is going to be px, probability of x. And then product rule for joint distributions, which is basically the same thing we did up here, but kind of in more formal terms. So if you take this, so this is basically the same value up here. You can see the arrow pointing to it. The joint distribution of rolling a particular dice roll and flipping a particular coin flip is going to be equal to number, so the number of occurrences over the total number of trials. And then if you sort of like separate that out and kind of like a chain rule thing, you can take, just number of occurrences over the number of occurrences for that particular number of occurrences of both those things happening over the number of occurrences for that particular coin flip. And then the not coin flip, sorry, the dice roll. And then the number of that dice roll over the total number. And then if you basically just split those two things out, then this first part is just the conditional probability of y given x. And the second part is just the probability of x happening in the first place. So then we can write this joint probability as just p of y given x times px, which is also going to be equivalent to p of x given y times py. And I think that's getting a little bit at Bayes' rule already. Yeah, let me think about if I'm going to explain it more later, or if I need to try to parse through that now.
No, you can just do it later because I think that was very clear.
Okay, so you can kind of see that this is equal to this, or like these
intuitively makes sense.
Okay. It's not super intuitive to me. I kind of just have to go with the formulas, but
I think it'd be more confusing if it was like more than two. I don't really understand the framework for that, but I can see it.
Okay. So we can talk through that as we go through. Okay. And then he kind of talks about independence here, and thinking about conditional independence and how that plays out. So I think I'll preface it by saying that, like, that if you're looking at like the probability, for instance, let's say you have like 4 different outcomes or 4 different variables. One is that you have a headache or you don't have a headache. One is that you have the flu or you don't have the flu. One is that you have a virus or you don't have a virus. This is very ill-timed. And then the other one is that you drink beer or you don't drink beer. And you can kind of think of this as that, okay, if all these random variables were independent, then this would just be equal to the product of all these individual probabilities. So like this would be equal to Yeah, so if independent, this would be like equal to pH times PF times PB times PD, right? But then if you have some conditionality, so basically that like some values relate to others in some sort of predefined way. So for example, if we have that, the probability of having virus given that you drink beer is independent, right? So it doesn't matter if you drink beer. So the probability that you have virus is basically just independent. And then if you think about another condition probability that you have the flu, given that you have a virus, and that you drink beer, is just equal to the probability that you have the flu, given that you have the virus. So it doesn't depend on whether or not you drink beer. So flu is independent of drinking beer, given the virus. And then probability that you have a headache is only related to the flu and drinking beer. Yeah, so you have some conditional independence based on, it's independent of the virus, given the flu and drink beer. Then instead of having this sort of total independence where you just multiply all of them together, you have some sort of like staggered independence. So you can basically break this up in sort of like sequence. So I'll kind of go through his, because I think the notation is simpler. So basically you have now that pH, the joint probability of just all these things happening. You can break it up first into pH given F, V, and D times probability of F, V, and D, and that just comes from our definition of joint probability here. So you have that it's like PY given X and times PX. So basically across all of these things occurring at the same time. And then you can break that down further because you know that this is independent of the virus, right? So pH given flu, virus, drink beer is independent of the virus. So you can just write that as this times that times this PFVD. And then you can break this down even further into just the flu given virus and drink beer times the probability of virus and drink beer. And then you can break this part even further, I guess both parts, even further, because this is independent of drinking beer, and the probability that you have the joint probability of having the virus, or joint probability of the virus and drinking beer, is just given by the conditional probability of having the virus given that you drink beer times the probability that you drink beer. And so you can sort of just break these things down sort of sequentially like this. So the final is like this probability that you have a headache given that you that you have the flu and drink beer, probability that you have the virus given that you have, probability that you have the flu given that you have the virus, probability that you have the virus, and the probability that you drink beer.
Okay.
The probability that you drink beer.
And that's assuming that, that's just the one assumption that the virus is independent of drinking beer. And you're able to break it down, or do we need to make all three of those assumptions?
You have to make all three of them. Yeah, so they're sort of breaking down this huge probability, this huge joint probability, using all this information. So you assume everything is true here.
Okay, and the overall test is we're trying to determine the probability of having all four of those things.
Yeah.
Joint probability. Okay. Is that joint? Yeah. Thank you.
Yeah, so I think the huge thing here is that like sort of so joint probabilities and conditional probabilities are related in this way. So you have if you have some joint probability, it's related to the conditional probability of one thing happening given that the other thing happened, times the probability that X happened in sort of in full. So that's one thing. And then on top of that, you have layered sort of independence. So like if you had that these two things were independent in the first place, you would just multiply them, multiply the probabilities by each other. So you have some like sort of layering in the joint distribution of both independence and conditionality. Okay. Okay, and then Bayes' rule. Okay, so if you have, so this we've defined already, probability X given Y is the fraction of the worlds in which X is true, given that Y is also true. So for example, if you have H of having a headache and F coming down with the flu, probability of headache given flu is a fraction of flu inflicted worlds in which you have a headache. So you say, how do you calculate this? So this is P of X given Y is equal to the joint distribution of X and Y divided by the probability of Y happening. And so that that basically just comes from this flipped, right? So like if I wanted to look at what the probability of Y given X, I just divide by probability of X on the other side, and I get that it's the joint distribution divided by the individual distribution of Y. And so from that, we can also say that this top part we know is also the probability of Y given X, because you can just basically flip these around. It doesn't really matter what order they're in. So the probability of Y given X times the probability of X. And so this is kind of, so from this, you can show that the probability of X given Y is equal to the probability of Y given X times PX as well. So this is the definition of Bayes' rule, which says that the probability of X given Y is equal to the probability of Y given X times PX divided by PY. So it's I guess it's if you sort of don't go through these steps, it's not obvious to see how the probability of X given Y would be related to the probability of Y given X. But once you see that it's sort of dependent on the joint distribution of both those things happening, then it's sort of easier to sort of make that connection that that the probability of X given Y actually does depend on, in some sort of strange way, the probability of Y given X. Or I guess in this particular way. And so so like I said, I don't think here we talk about how it's useful, but there's like a whole field of like Bayesian like statistics and like Bayesian machine learning that people are like using this rule to like do really interesting stuff. This was like I think a pretty fundamental part of learning. And then what is this last step here? PX, PY, PY. Okay, yeah, I'm not really sure. I think this is just showing that you can get this PX given Y from this as well. And I'm sure you can do the math to show that. But yeah, we'll leave that as an exercise. So basically Bayes' rule says, okay, if you have P headache given flu, it's equal to, I'm just gonna go down here. You can do the intermediate step, but it's equal to P flu given headache times P headache divided by P flu. And so there's some other cases. I think I would write this as like other forms really, rather than other cases. So this is Py given X is equal to Px given Y times Py divided by Px, and it's just written in a different way. So it's written as Px given Y times Py. So basically, so all the times that, so basically the joint distribution of Px given, or Px and Y, and Y plus Px and not Y. Okay, that's not clear to see. Let me move it somewhere else. So this is Px Y plus Px and not Y. So yeah, so you can see how we can write that as Px given Y times Py plus Px and Px given not Y times P not Y. That's just the sum of all the Px's. And then Py given X is equal to Px given Y times Py divided by basically the same thing, the sum of all the Px's. So here it's written as X given Y times Py for all different possibilities of yi. So you're summing over all the possibilities. So this is kind of, yeah, they're kind of the same thing. It's just written in different ways, I think. So this is the sum of all different y's, and then this is just saying there's maybe two values of y's, and either y or not y. And then it kind of gets a little complicated when you go into like multiple variables, and I wasn't super, I guess I wasn't super clear. I mean, it is kind of clear, but I wasn't clear about like how much you could extrapolate from this. So I'll just kind of talk about it, and then we can kind of wrap and see if we have, if we can get some more insights from it. But Py given X and Z, or the joint probability of X and Z, is going to be Px given Y and Z times Py and Z divided by Px and Z. So I think from just the, so if I just write the Bayesian form here, given X equals Px given Y times Py over Px. Yeah, so just from like the two variable form, you can kind of see if you like substitute, like y for, yeah, so like on the right side of the equation, if you substitute y for yz, like you can see how things fit in, and x for just, yeah, x for, yeah, I don't know. So it's kind of tricky to see how it works with three variables, I think. And I'm not quite sure like if that also means that this is equal to like P Z given XY times P XY divided by P P of XZ. Yeah, I'm not sure like how that works.
Yeah, I would need to see the derivation to really understand that. I think for now I'll just trust the equation, but I think without seeing it derived, it'd be hard for me to determine if that identity is true.
Which one are you talking about?
No, so just the third one.
Yeah, so for like this third case here, I'm not sure how we can if we can extrapolate from this sort of Bayesian derivation to get to like this. Is this probability also true?
Oh, I think that this is just something you have to see a few times to realize what's happening. But it's essentially the same thing, except instead of only being given one variable, you're given a joint of multiple variables, and so the Bayesian rule still applies. And instead of multiplying the conditional by the probability of that variable, it's the probability of the joint of all the variables that were given. But it's essentially the same formula otherwise.
I see. Because this is still, so this is py given xz is still equal to p basically xyz over p xz, then
Right.
yeah, okay, yeah, I see. So that is true then, because this pxyz can also be written as p of z given xy times p xy.
All right, so you just derived it. Nice.
Yeah. Okay, yeah. So I think kind of think about it as a joint distribution first. Is useful to think about before you like go to Bayes' rule.
And then you relate it to conditional with our product rule.
Yeah.
Anyway. Actually, could you just go back to the original Bayes rule, please, just so I can look at it one more time? All right, thank you. I'm good.
Okay. All right, let's keep moving. Mean and variance. So I think this is going to be helpful for the homework if you've looked at the problems yet. And you'll remember from the CME stuff. So we defined expectation as the mean value, also known as the center of mass, also known as the first moment. And so the expectation of a function or probability function g of x, I guess a probability density function g of x, is given by the integral over all x's of g of x times the probability of x at that sort of particular location. Yeah, and then over all x. So for example, if g of x is yeah, I guess let's use the binomial distribution from earlier. So if g of x was equal to 1 over b minus a, then you would just basically plug that in, and then you would multiply by the probability of each x, which is going to be, sorry, this is the uniform distribution, not the binomial distribution. Uniform distribution. So if wait, does that make sense? No. Times x itself. Wait, no. What am I saying?
I think the probability is going to be 1 over b minus
yeah.
a, right?
Yeah, so then g of x is probably just x.
But I think you can't write g of x like that because you need some function g of x that is true from negative infinity to infinity, right? But that's only true between a and b. I'm not sure how you do this for uniform distribution.
Well, no, that's fine because you can just basically replace this negative infinity with your bounds, the bounds that you actually have.
Okay.
So, but I think so. I guess that would be yeah. So I guess that would be the mean of that would be from a to b, x times 1 over b minus a, right? Dx.
And why are you multiplying by x?
Okay, so then I guess g of x is actually a function of the random variable x. So you can think of g of x as like some scalar times the random variable or just the random variable itself. So forms of g of x is just going to be either x or maybe you have like some function of the random variable x. Maybe you have some matrix function of the random variable x, etc. So and then the probability is the probability density function or whatever, as it depends on x. So I was wrong by saying g is the probability density function, p is the probability density function, and then g is just some defined function of the expectation that you're looking for.
Okay, thank you.
Yeah. And so this is the first moment. So basically, you can think of this as like x raised to the 1, whereas you can have like the nth moment, which is when you define g of x as x raised to the n, nth central moment, which is where you define g of x sort of centralized around the sort of first expectation, or the mean value raised to the n, and so on. And so the mean then is defined just as the expectation of x itself, which is just this the integral across all x of x times px. And then we have these two properties here. I think linearity and I guess scalar multiplication. So basically, that if you take a scalar and multiply or if you take the expectation of a scalar times the random variable, you get the scalar times the expectation of the random variable. And then if you have a sum of the scalar plus the random variable as the function of your expectation, then it's going to be the scalar plus the expectation of your random variable. And this is kind of obvious if you just think of this expectation as mean, right? So if you shift the mean by some scalar, that's fine. If you scale the mean by some scalar, that's also fine. And it doesn't really change where the sort of mean location is or what the mean is.
It sounds like mean is just the first moment.
Exactly.
Okay.
Yeah, so I guess this actually is a general definition of expectation, and they maybe shouldn't have put this mean thing here. But when you take just the first moment, when you define g as just x, basically, then you have the mean. So this is only when g of x is equal to x. Okay. And then we can also define variance as the second central moment. And so that is defined as, so here we had the nth central moment definition. So now our g of x is x minus mu, so the expectation of x all raised to the second power, so squared. And so the way we get this is, you can think about this as like just multiplying that through. And so you have expectation of x squared minus 2x. So I'm just multiplying this inside thing, x minus expectation of x squared. So that's the inside thing. And then taking the expectation of all these is now going to give us ex of x squared minus ex I guess let me just simplify. So 2ex and ex minus ex squared. And so the reason why so you'll note here that the expectation of the expectation is just the expectation. And so we can kind of show this like this. So ex, so expectation of expectation is basically equal to the expectation of the mean, right? So that's equal to integral of the mean times px dx. And that's equal to, if we just pull out the mean as a scalar, integral of px dx. And the integral of the probability should be equal to 1 across all x. So then that's just equal to mu, which is equal to the expectation. So that's how we got this ex. Ex should be just ex times ex. And so if you multiply that out, or if you sort of simplify that, then you have ex squared minus ex squared. Okay, and then if you kind of go through and do the same thing for like plugging in these different scalar and sum, you can show that these two properties hold, so that if you have the variance of a scalar times x, it's going to be the scalar squared times the variance of x. And for linearity, if you add some scalar to the random variable x, the variance is actually going to still remain the same. So the adding a scalar to the random variable doesn't change the variance of the random variable. And that kind of makes sense intuitively. Like the standard deviation doesn't change because you add some scalar to all the values.
Oh, so like
yeah.
What the variance is like how much does the random variable x deviate from the mean, right?
The variance, is that what you're asking?
Yeah, like from a conceptual standpoint.
Yeah.
Okay.
Yeah. Yeah, I guess. Yeah. How much? Yeah, that's a measure of how much it deviates from the mean. Squared, right? Because you have x minus. So that's in a first order approximation, you can just take x minus the mean, and then sort of in a second, a higher moment approximation, you can raise this n to the 2 instead of 1. And I guess we've found throughout history that maybe it makes more sense to to raise it to the 2. I'm not quite sure why. Yeah, I'm not quite sure why we take the second central moment instead of the first central moment. But it's still the same measure. It's still a measure of how far you are from the mean. Okay, and then now we get at covariance here a little bit. So there's still this linearity still holds even if you have two random variables. So you would still have the expectation of one plus the expectation of the other. And then for covariance, if you have two if you have two random variables or like some joint distribution, then the covariance is defined as the first. Yeah, so the covariance is defined as instead of squaring the central moment, you take the central moment of one variable and you multiply it by the central moment of the other variable. And you can do a similar analysis like we did here to show that that is equal to the expectation of the joint or the product of both the random variables. So this is like E, where it's like your G x y is equal to x y minus like the means, right? So like this is mean x and this is mean y. So you can kind of, I won't go through the math of that, but I think you can show that using a similar analysis as here. And you kind of see it even a little bit. You can see that this x squared is now like xy, and this ex times ex is now ex times ey. And then the variance, so that was covariance, and then the variance of x plus y is the variance of x. Why is it doing that? The variance of x plus 2 times the covariance of xy plus the variance of y. And so if you look at like a matrix of the covariance matrix is what we call it. Covariance matrix. In the what's happening?
So covariance is a measure of like how related two variables are to each other, right? Like how.
Yes.
Okay.
Yeah, so I think you can think of it as sort of like a measure of like independence between them.
Got it. Okay.
Yeah. Yeah, I'm trying to think of how you can see that from the equation. Yeah, it's not clear to me how you can see it from the equation, but
yeah, not that. I mean, it's not that clear. Because like if the variance of like, or I guess like if you're looking at like the variance of two random variables summed together, that would be what you're doing is like you're trying to find out like, I guess like how I don't know.
yeah.
I can see like I get how the derivation ends up with the variance of x plus 2 covariance of xy plus variance of y, but like I'm trying to conceptually understand.
Yeah.
Like why, like how a singular, like how like a random variable x and a random variable y, and like how far away they are from the mean, or to some degree n, would sum up, and you still take into account how they vary from each other, like how independent they are from each other.
Yeah, I mean, we talked about this a little bit last time. Yeah, I think the idea, right? If you, Kevin and Stu, like, um, is that the covariance. So if we looked at like, yeah, like how can we see this sort of like in the picture? So if you have like X and Y or something like that.
Mm-hmm.
Oops, these are terrible. Yeah, what is the covariance? Like, how can you picturize it?
Because like the variance would just tell you like how far away that x is from its standard deviation.
Yeah.
And how far away that y is from its, or I mean from its mean.
Yeah.
And the covariance would just be looking at like how related, or so I guess maybe the overlap between the two.
That's what I think, but I'm not sure.
I think the way I think about it is that because you can also have the variance of two variables, right? I think what you're describing might be variance, but covariance is variance taken to the next level. Because so you know that these are random variables, so there's multiple values of x and multiple values of y.
Right.
If you were to just do the variance, it's essentially the standard deviation squared, I believe, standard deviation squared of all those values. So it's how are these variables varying with respect to each other. Covariance is looking at all of the different dimensions as well. So if we have a matrix, I think I mentioned this last time. Let's say these are not values, but these are vectors with 3 dimensions. Then the covariance matrix is going to be a 3x3 matrix, and you're going to be looking at the dimensions with that dimension with respect to another dimension. So we talked about this before, but if you would look at the matrix, 3x3 matrix, the diagonal would be the standard deviation, and then the other off diagonal would be, well, I guess with x, y, it's a little bit right, yeah. With more than 2, it's probably easier to see, but it would be sort of like that. So you're looking at amongst different dimensions or amongst different variables.
So can you give an example, like what these? Yeah, can you think of an example of like what these different X, Y, Z's could mean and like how they might relate to each other?
I mean, I guess an image. If you look at like a 3-channel image, you'd have your like height, weight, like your height and your width of your image could be like your x and y, and then your z would be an RGB channel value. So you can see like how related a singular pixel is to its neighbors or something like that.
Or I guess we can kind of maybe just think about these, like, so if we think about like these things, right? So like the headache versus like the flu. So there's probably like if you took a sample of like people who had headaches and people who had flus, well, maybe two. Maybe
Yeah, I feel like that might not be as good because it's like those are discrete. But if you did like maybe if it was like level of headache, maybe the temperature of your I don't know fever, and then virus count of your flu, and you want to see, I guess, I guess you're trying to get an understanding of like of people with both a fever and virus count, like what is the spread of possible outcomes?
Mm-hmm.
Is that a way to think of it? Like, what are the spread of possible values? Like, are they like close together? Like, if you have a fever and a virus, then you're likely between this number of, I guess, this temperature value. And I don't know. Actually, I just don't understand. But I don't think it works with discrete values.
Yeah, what Kevin was saying, I guess what you're describing would be variance, right? Based on your examples and stuff.
But I think covariance, you need to take into account. You need to take it to the next level. So like you're trying to understand. Maybe you're right.
So it's basically like some three-dimensional thing, right? So you have like some like, so if you think of just like normal distributions, you have some distributions on like each one of these axes, and then there's some like intersection. So like this is like some 3D thing, and there's some intersection between X and Y, some intersection between X and Z, and then you're looking at like the variance in between, like the inside the intersection.
Okay, that makes more sense. So that would
think.
That would be covariance.
Yeah.
You're effectively comparing one dimension to another dimension.
Yeah, it's like you're looking at the spread of like is that right? Yeah, you're looking at the spread of
the intersection, kind of, or in that two-dimensional intersection.
Yeah.
And so I guess with greater variance, you're saying that two-dimensional, or I guess greater covariance, the bigger your two-dimensional intersection is, right? The more possibilities there are in there.
Greater covariance would be the like I guess the greater the intersection is, possibly the greater the spread might be.
Oh.
But it's a measure of spread.
Okay. Okay. Can I also use the word number of possibilities within the intersection?
Yeah, I guess so. But I think not.
Maybe not.
Not quite, yeah. Because it's more spread. I think that's the important part. It's like it's about some measure of spread.
Yeah. So I guess I had always thought of covariance as a measure of relatedness between two random variables.
Yeah.
So if a random variable can take on a spread of values, then you're saying that the larger this covariance value is between these two X and Y variables or random variables, you would be saying that the more related they would be based on the intersections of the spread of values. Is that fair to assume, or is that incorrect?
1 second.
I guess highly relate. I guess yeah, it makes sense. Like the higher your covariance value would be, the more related these two values would be, because there is more area.
Yeah.
There's more total area between these two values that X and Y, more values that X and Y could take on that fall within all possible sums, or all possible intersections of the two values.
Yeah.
Yeah, I feel like maybe one way to think of it is if you have two different variables, and if you were to you can have some maximum possibility if you were to I'm trying to think of it in terms of words, but I imagine like covariance is some subset of all the total possibilities, and the greater the covariance, I guess the bigger that inner subset is relative to the total subset until you get to the limit where I guess the covariance between the same variable is just
One.
all the possibilities.
Or yeah, like all the possibilities.
So that'd just be the variance of x or whatever. Whereas if there were no intersection at all, then your subset, your small circle is like, no, it doesn't exist. So like you have no range because there's no intersection.
Hey, Kev, can you like provide an example of how covariance is used, like in a machine learning application? Like, I guess like is covariance something that you're using to determine like, I guess the relationship between things or like different features or something? Is that like what it's normally used for?
I believe it's used in Gaussian mixture models, which are, it's almost a form, well, it's a form of clustering.
Okay, that makes sense.
But just more based on probabilistic theory and the probability of certain samples being derived from certain Gaussian distributions. Or in general, just like the more statistical algorithms typically use covariance.
Yeah, because if you're trying to think about how two things that or two random variables are related, you would have to use covariance. That's basically the only metric that you have. So I see it being useful for clustering.
Some problems and just get a little more like clarity.
Yeah, maybe I think as we dive deeper into machine learning, maybe it'll become a little bit more obvious. But right now, I think we have a basic understanding of it. Okay, so let's try to move through the rest of these. So Gaussian distributions are very popular and very representative of a lot of things that like happen in the world. So they're represented by like this equation here, and they just have like this form where they look like a bell curve kind of. And so, let me see, I wasn't really sure what he was writing down here, so.
You can skip it.
Yeah, I think I'll just skip it. I think basically he was getting at like how you find mu and sigma, but not sure. And so you can even take that to, so you can take this Gaussian distribution to a sort of multi-variable plane. So this was kind of just getting at like when you have one, this is kind of defined for one variable. So you have x minus your mean, and then you have your standard deviation of x as sigma. But you can think of this as like xy instead now. So that now this x is like your xy, right? And so you maybe have some matrix of means, and then some covariance matrix, like as we defined above. Right.
There's a matrix here.
Yeah.
Oof.
So yeah. So basically, it's the same definition, but now with a matrix instead of like simple values. And so so then what that looks like is I'm not sure what this n is. Oh, number of.
Maybe it's the number of variables that you're evaluating for x. Real.
Yeah. Yeah, maybe it's the number of variables.
I don't know if that makes sense.
What are you talking about? Sorry.
I'm talking about when you have a multivariate distribution, and you're putting these. You're basically finding the probability, or finding the density function using those matrices. Does this 2 pi? So this was originally square root of 2 pi.
Mm-hmm.
So basically 2 pi raised to the 1/2. And now it's written as 2 pi raised to the n over 2. Is the n the number of variables? Number of random variables? I don't see why it would be. It should still be 1/2.
It's the number of variables. Yep. It's yeah. It's the number of variables.
Okay. So if you had 2 variables, it would just be 2 pi.
Yeah, because I guess if you had the 2 individual distributions and you multiplied them together, I guess this is a little trivialized, but the constants, at least, it would be square root 2 pi times square root 2 pi, which would become 2 pi.
Yeah, that makes sense. Okay. Yeah. Okay, yeah, so if you literally multiply the distributions together, yeah, that makes sense.
Yeah, but it might not be that simple, but in terms of the constants, I believe it is.
Yeah. Yeah, so then you have that, and then you take the basically effectively the square root of the covariance matrix. Because remember, I guess the covariance matrix, actually these things squared. Not that one. That's not actually squared, I guess. This is squared. Yeah. So So you take the square root of that to get like basically the simple standard deviations, and then you just basically plug in the same thing, but now you're taking the inverse of sigma instead of dividing by this 2 by the I think that kind of makes sense. But you can kind of play around with this, maybe with some numbers in MATLAB or something, and see how it looks. But yeah, that's kind of the idea when you take this into multi variables, which I think are more useful than the single variable distributions. Yeah, and so here's the definitions of the matrices, or the values. So like mu is just the expectation of x, whatever x is. And so I think sometimes people will use okay, never mind. But yeah, so these are just the definitions of these things. And so you can sort of generalize this as like covariance of x, and you'll know that in the sort of diagonals, you'll get that you'll have x times x and so on for your variances. And then there's some definition here. Maybe this guy came up with this thing. And so this is defined as the Mahalan-Obis distance. Tons of applications. I don't know what that is. I don't know what that is. I don't know what that is, but I know what Kalman filters are. Kalman filters are really useful in controls. So we talked about this in my math class a little bit. Okay, and then sort of going into like transforming these variables, these these random variables. So like we know that linearity and scalar multiplication is going to be okay with expectation. So you can basically, if you have some let's say line you're trying to fit, or some distribution you're trying to fit, and you have some A as your some parameters and some B as your measurements, and you're trying to basically estimate you're trying to estimate some maybe you're trying to estimate a distribution here or something. But anyway, you just know that if you have some distribution where you have ax plus b, and x is your random variable, a is a constant, and b is a constant, you can write this as in this form. And then for the covariance, it's a little bit different. So in this case, remember that the scalars, the addition of a scalar doesn't change the covariance at all. So basically this is effectively just like covariance of ax. And in that case, it's a times the covariance of x times a transpose, given that these are matrices. So that is analogous to the squaring of a scalar, as we talked about here. So the variance of a scalar times x is equal to the square of that scalar times the variance of x. And in this case, this is almost like squaring a matrix when you multiply by a and a transpose on the other side. Okay, and then this means that for Gaussian distributed quantities, where so they usually write a random variable x that's a Gaussian distribution as like this like little symbol times this little symbol n of some mean and some covariance function. And so that if you have that, now the random variable or the way you're estimating or the way you're fitting a model is ax plus b, or you have some model ax plus b where x is the random variable, then you know that it's also going to be randomly normally distributed around these quantities. So you just take the expectation of this and plug that into your normal distribution, and you take the covariance of this and plug that into your distribution. So sort of like, going from around the random variable x to around this distribution around this model ax plus b. But it's still, the important thing to note here is that it's still normally distributed, but now it just has a different mean and different covariance. And then sort of like stemming from that, the sum of two independent Gaussian random variables is also going to be a Gaussian random variable. And these are sort of like important things to keep in mind. So if your y is equal to x1 plus x2, where x1 and x2 are independent, then you'll have y, the mean of y is equal to mu1 plus mu2, and the covariance of y is equal to covariance of 1 times covariance plus covariance of 2. So this is for independent. I think that's important. And then the multiplication of two Gaussian functions is another Gaussian function, although it's no longer normalized. So I think that means that it's no longer, I'm actually not sure what they mean by normalized here. I guess it, well, let's just look at this. So they're saying that if you have a normal distribution with mean small a and covariance big A times a normal distribution BA, you get a normal distribution around little c and big C, where big C is A inverse plus B inverse, and then that whole thing inverted. And then little c is C A inverse A plus C B inverse B. Yeah, I think it's just going to take some more like looking up stuff to like figure out how that happens, that I have not done yet. So I think this is more into the intricacies of how Gaussian functions work, but I think it's figure outable, if you need to know it. But I guess just the thing to know is that it is another Gaussian function, so it does have some normal distribution itself, although it might not have the same normalization as the initial two things that you're multiplying, two distributions that you're multiplying. And then something that's like, I think pretty important in terms of probability and statistics is like this central limit theorem, that basically says that like, if you take enough samples from, if you take enough samples from like basically, I think any distribution, it's going to follow a normal distribution. So here we have a distribution, probability mass distribution of biased dice roll. So you're saying that instead of these having basically the same probability to occur, you have some loaded die or something that has these probabilities instead. And let's say we're going to select samples from this, having a size of n equals 4. So we're basically going to like say, okay, 4 different rolls essentially, and we'll sample that way. So then in this case, you have like the first sample is 1 1 1 6. So what's the expectation of 1 1 1 6? It's that. What's the expectation of something else? It's that, and so on. You keep doing it, keep doing it, keep doing it. The idea of central limit theorem is that if you do that enough, regardless of the probability density function or probability mass function, you're going to follow a bell curve distribution, normal distribution. So this is why like normal distributions are so useful, because basically so you see like the mean is what the mean would be if you just like basically added all these up and divided by 6. But yeah, so the idea is like a lot of things in nature, if you just basically sample them enough, will have a normal distribution. And I forgot who came up with this, but it's pretty useful, I think, in probability and in like real life things happening. Okay. And then maximum likelihood estimation.
Well, one quick thing about central limit theorem. Okay. The central limit theorem is saying that the expectation will follow that bell curve, as opposed to, right? Because like we're taking the expectation for each one of these samples, right? And then we plotted the, I guess, probability distribution, which is
well, I guess it's saying that the distribution of the samples will follow a normal distribution. So the distribution of the samples is going to be given by this like 1 2 pi sigma. Like you can fit it to something like this is what it's saying. What is it? X minus mu. Yeah. So not necessarily that the expectation is going to be the expectation of this well, no, that is true. The expectation is going to be the expectation of this distribution. But more general, that the distribution itself of all those samples is going to follow a normal bell curve distribution.
So you're saying that basically, even though you have something that like weighted dice, where it's going to be biased towards certain values, if you sample it enough, it will eventually still, regardless of the weighting, provide you a normal distribution.
Yes.
Got it.
Yeah. Yeah, it might be a little counterintuitive. Now that I'm thinking about it.
It makes, to me, that only makes sense if the normal distribution is of the expectation, as opposed to a normal distribution of just the numbers. Yeah.
Yeah, this is saying that it would be the actual independent random variables when summed would actually be in a normal distribution, even if the original variables themselves were not normal. Yeah, so it's unintuitive, but it seems that it will always come back to a normal distribution of some kind.
Yeah.
Properly normalized sum. I think part of the reason is inaccessible for me right now, just because I'm not very familiar with the language yet. So maybe more reading will make more sense.
Well, just think about it like the way that the dice example in the lecture just now. Every single like sample was a set of values for that random variable.
Mm-hmm.
So it's just saying that when you sum all of your samples for a set, if you do enough samples, you'll eventually get a normal distribution.
Right. So
it's not so much like saying that, okay, I have a weighted dice that biases towards rolling 4s, and then I do 6 rolls for one set, and I get like 3. I'll get like 4 4s. In that case, yeah, if I do that enough times, like, or if I looked at the sample, I'd be like, oh, look how many 4s I got. That wouldn't look like a normal distribution. But when you do the sum of all of these like sets of samples, you'll eventually get a normal. So I can see how that would work.
Right. I think the key there is you have to do something to, right, each set. Either in this case they took the expectation, but I think generally you have to normalize them in a way such that they're comparable across sets, and that that's going to be the curve that we're expecting.
Yeah. So I think yeah, I think in this case it's not necessarily important what the mean is and what the variance is. So like the mean could be here, for instance, if the dice are loaded in another sort of way. But the idea is that it will have like sort of some normal distribution.
But I think the key for me is that like they've made the sets comparable by normalizing it with some function. And I think, I'm not sure if I'm misinterpreting this, but my interpretation is that here they normalized it by taking the expectation, whereas you could also just sum up the values and whatever normalizing function it is. When you look at when you normalize all the different sets, and then you take the distribution, that is a bell curve.
Yeah, it definitely needs to be normalized. They're properly normalized sum, yeah.
I don't. Oh, which is the mean.
Okay. And then last thing, maximum likelihood estimation. So there's, I guess, 2 definitions given here. So probability is inferring probabilistic quantities for given fixed data models. So for example, probabilities of events, marginals, conditional distributions. And it's statistics is inferring a model for a given fixed data observations. So inferring probabilistic quantities, whereas you're inferring a model. So clustering, classification, and regression. So for this maximum likelihood estimation, we make the assumption that the random variables are independent and identically distributed, which I don't actually know what that means. But I think I can extrapolate that probably means that, like, for example, they're all normal distributions, for example, or they're all uniform distributions, something like that. So for example, let's say we're flipping a coin, and so the objective function of these, as they've written here, is the probability that you get one thing. So the probability is given by, like, the probability of success in this case, and xi is the outcome. So the probability of successful outcome times the probability of a failure times the number of failures. So where xi is 1 or 0, or heads or tails. Okay, and then you do a bunch of trials of this. And yeah, so you do a bunch of trials of this, and so you want to find the probability that, let's say you had 5, so you hold on, let me think about this. Yeah. Is it just 2?
Are you looking at the likelihood thing?
Yeah, I'm looking at this L function.
I guess it looks like the joint probability of our random variable being equal to whatever we're defining, x1 to x9. So does that mean those things happen sequentially?
Yeah, that's what I'm struggling with. If it's like, I'm not sure if they're talking about, like, for example, flipping 10 coins and, like, x1 being 5 heads and x2 being, 6 heads and so on, or if it's like head, tail, and so on.
Yeah, I took it as each x1, x2, x3 to xn is an event that you've done. So it's either a 1 or a 0.
Okay. Yeah. Okay. So let's take it as that. So the joint distribution of, like, each independent event being either a 1 or a 0. So let's say you've defined some set of outcomes. Let's say you wanted x1 to be heads, x2 to be tails, x3 to be heads, and so on. And you want to find out what the probability is that you actually get that outcome. Okay, so then you make the assumption independent and identically distributed. And so then you can write this as just the individual probability. You can write the joint probability, joint distribution, as just the independent distributions multiplied by each other, because they're independent. And that's equal to the objective function just multiplied by each other. And so now L is, or yeah, I guess the likelihood is now just a product of each of these for all i's. And so that's expanded out here. And so now you can write that out even further, as now all these different, so the product just written out further. And so for this, they kind of use sort of one of our sort of math rules where you have, if you multiplying exponents together and they have the same sort of base, then you can just sum them together. And so you have sum of xi's time, so pi raised to the sum of xi's, 1 minus p raised to the 1 minus xi. And then it says we don't like multiplication, let's convert it to summation. And so what they do is they take the log of the entire likelihood function. And so now we define log of LP as this little LP. And so they have log of P, sum of this, sum of the x's across n, and log of 1 minus p times the sum of the 1 minus x's. So yeah, to sort of recap, now we're looking at the likelihood function, and we've defined now a function that that's the log of the likelihood, which is basically going to still capture the likelihood, and we've now defined it as a sum of like two different things. And so now we can optimize p, right? We can optimize the probability that will give us the maximum likelihood, right? And so the way we do that is by taking the derivative of this function with respect to p and setting it equal to 0. And so yeah, you can take derivative of this function with respect to p, and apparently that is, yeah, because if you take the derivative log, it's 1 over p and 1 over 1 over p. And then these sums don't have anything to do with p, so they're not going to be, so this is the partial derivative with respect to p. So this is the derivative, set it equal to 0, and then solve for the p that'll give you the maximum likelihood. And so it turns out, if you kind of go to the math, it turns out that the p that gives you the maximum likelihood of like these events happening, right, is going to be equal to 1 over n times, for this particular distribution, this Bernoulli distribution, it's going to be equal to 1 over n times the sum of the xi's. So you can do this for basically any distribution if you want to find out how to optimize the probability to get the maximum likelihood of your event, of your outcome happening. And this is just a simple example for like the Bernoulli flip of a coin. And I think this is going to be basically just like, so if we summed up, so the xi's are 1s and 0s. So let's say we had, yeah, I'm not sure what this like means in terms of application. So if we had, because it's not like we can like fix the probability per se. It just tells us what the optimal probability would be for that specific scene of events or outcome of events.
Yeah, sequence of events.
Sequence of events. P is the parameter that's going that's used in Bernoulli. So you're maximizing the parameter. You're choosing the parameter that maximizes the likelihood of the distribution.
But you don't get to choose that, right?
Yeah, I mean, yeah, you can. If it's a fair coin, it's going to be, P is going to be 0.5 always. But if it's not, and let's say it's 0.2, and then it's usually you flip it and it's majority tails all the time, then P is not going to be 0.5. It's going to be something different. But you have to do this MLE optimization to find what that parameter is that's going to maximize that likelihood distribution. And in this case, it's the average of all the points, or all the actual samples.
Mm-hmm. So do we use the word likelihood to define what are the odds that we get the sequence of events of successes? Or, I'm not sure if I understand what likelihood means.
Yeah, I think that's exactly right. Likelihood is what are the chances that this sequence of events happened.
Okay. Oh, perfect.
Whereas I think probability is like this one thing. What's the probability of like heads or tails?
Okay, so
probability of heads, for example.
Probability is better for events, but likelihood we use for sequences of events.
Sure.
Not exactly. I think probability is more intrinsic to the distribution, what is the probability of this happening, what's the probability of that happening. The likelihood is, let's say you did an experiment and got these results. What is the likelihood of repeating those results or getting these series of samples that you got from your tests?
So
okay.
Probability is inherent to your system. Likelihood is an abstraction away from your system. It is like, what are the odds that my system is going to give me this output in this order?
Right. Given that you already have done some experiments, right?
Right. Yep.
I see.
That makes a lot of sense. That's why you see like MLE is like a really core concept in a lot of like machine learning.
Yeah, I'm still struggling with the application of this actually.
It's like if you, because I guess the idea is that like you have like data, right? So you can have some structured data, and you don't necessarily know how to replicate the results of that data. So you would train a system using MLE or like as a metric or whatever to see how likely could it be that I could replicate those results again, right? So it's like you might go, I don't know, like I don't know what a good example is, but anything where there's like a process where you collect data for something, and then you want to see if actually this is not a good example.
I was thinking maybe if you got some weird results from your system and you want to like, was this a random occurrence or not?
Yeah, that makes sense from like the likelihood perspective. So you can calculate the likelihood of those results happening.
But then it gives MLE gives you insight into your system. Like this would only like the odds of this happening, or in order for fuck. Actually, you're right. I don't know.
Yeah, so I mean, I get that. So you get some data, right? And you originally, so I think likelihood, when you already know the parameter, like you already know that it's 50%, like makes sense. Like, so what's the likelihood that I actually got these outcomes when I knew that the probability was 50%? But I think going the opposite way is like, what this is trying to do is like, how do you optimize this parameter to get the maximum likelihood possible? And
more data happening.
Sorry?
Yeah, like what you were saying, it's like it's how do I optimize this parameter p, which I don't know what the value should be or what it could be, that would result in the data that I just saw, which is my sequence of events.
Yeah. So I guess this is happening. Oh, I guess. Okay. So this is where you don't know. So this is where you don't know the parameter, but you know the distribution.
Right.
I see.
Right, because like it's easy to say that you would know if it's a fair coin, then you know what your p-value is. But how many real-world systems do you really know what that optimization parameter should be? You don't, right? But you can assume that, like, you know what the distribution may be for a lot of like real-world systems, just from nature. And so maybe that's the point of maximum likelihood estimation, is that I've done I have a data set where I observed a bunch of like a bunch of features or like whatever, and now I want to know, how likely can I repeat these events? Like how likely can I reproduce this same set of data in the same sequence again? But I don't actually know what p should be. So can I optimize? Then maybe you just take the maximum likelihood.
I think I have a better way of saying what I was thinking before. It's like, we're basically, this might tell us if our system is like, a fair coin or not. So you'd expect it to be 50-50 maybe. And if you optimize P and you find out it's like 0.2, then you're saying that like your system is not like randomly behaving. It's like biased in a certain way. And so now you have insight into the behavior of your system.
Mm-hmm. That makes sense.
That makes sense.
Okay. So we've reached the end of our time.